All right. It's 8 o'clock. Let's start our session. Do you hear me, Hannah?
Yes.
Okay. Let me volume up. Okay. Before starting today's session, do you have any question about the previous session or any topic or content that we discussed last week?
I have a test tomorrow actually on electrostatics, the whole unit. And I have a really quick question about continuous charge. Like I know the electrostatic force between like two separate particles. That's just Coulomb's law.
Mhm.
But I was reviewing for like a disk and for like a line. Of like continuous particles, and I was wondering how you would find the electric field for that.
We already tried the formula, so I can you just be more detailed about your question? What is your the question? So, do you want to know how that line charge or discharge connected to the single particle charges? That's what you're asking?
I'm a little confused how to compare them to each other. So I saw an example problem where you had to rank the electric force of four different situations. One of them was just like two particles. Another one was like three particles, and it was asking, and there's another one where it's just a continuous line and another particle. So it's saying like what is the ranking of the electric force or electric field on them? And I was confused how you would be able to kind of compare and rank the different ones.
Well, you gotta just estimate the Coulomb force out of two different charges with a different distribution of charge density. So if you assume that just total charge they're same, then it depends on how that force actually spread over the given space. So basically, if you force it just concentrate on the same direction, that might give the maximum magnitude of the force, but that charge distribute over the line or disk in a given space, then that individual charge element divided by the overall volume should produce that the force in different directions. So basically, now you have like you have two point particle in one dimension, and plus and minus. All the force actually line up in the one dimensional space. That four Coulomb force only pointing in the one direction. The total force of the Coulomb charge only in this direction. So if you assume that this one Q1 and this Q2 they are same quantity, then total force out of two charges only in the one direction. But if total amount of charge is same, but it just distribute over the line, then the charge, total charge. Now you just change that, point particle to the line, one line. Then that all the line segment spread that force into the two dimensions, right? So individual force will have different amount of Coulomb force out of the line segment. So instead, all the forces point in one direction. That means the overall magnitude is line of the one, you know, the vector component. Now you have like forces spread over multiple directions. So if you're only looking at the force in one directional vector, then that amount of force from this charge onto this point particle will be smaller than, I believe, than point charges, because that all the forces is this direction will cancel out each other, only leave that the this direction. But that small amount of like the point charge with the charge density will obviously smaller than two particle case which has the all the charges sitting on the one spot. Same thing, if you just spread your charge over two-dimensional disk space and you total charge Q the same as Q, but you have to divide by overall volume or surface area A, right? So that one element out of that surface, if you this one, so let's compare. This one has like a, well, there's one area, so that is one. I'm just giving you some kind of random number, and this one has maybe the length of this one is 10. Then the point the effective point charge on this spot will be 1 over 10, right? So you have 10 times smaller Coulomb force applied to this test charge. If you expand the concept to two-dimensional space, then this might be like the area of this one is 100. Then your charge density with Q divided by 100. So they'll only have 1 point out of 100 produce the Coulomb charge onto this test charge. Then you may end up with the 100 times smaller force applied to this point charge. So if you compare, I guess, three different cases, in the case you have all the forces sitting on the one particle, may have the strongest force, Coulomb force in the direction. And you have line charge in the middle of actually, this line only contribute to create Coulomb force on the test charge Q. And you have a large area of the surface, but you have like total charge Q, this one Q2 and this one Q. Then that just produce maybe like 100 times smaller Coulomb force. This is case one. I mean, this is case one, this is case two, and case three, where the point charge 3, then if this line charge 10 times longer than this point charge, then you have 10 times smaller Coulomb force. If area is 100 times larger than this point charge, then that should be, oh, that should be actually 2. This should be 1. Then that should be 100 times smaller Coulomb force. Now the constraint is all the total charge of the point point particle line and area is the same. So then make your charge density inside the surface, inside the line, under this particle, all different. But well, if you have like 100 times or 10 times more charge on the surface of area and the line, then the effective Coulomb force should be the same. They all should be same. So it is pretty much depend on the charge density.
What if they don't give you the charge density? It just gave me like scenarios where you have like 2 points and then 1 point and like a line, and it says which one is greater essentially.
I can't compare it without the information of total charge and area.
So
there's no way. Like obviously the Coulomb charge depend on the charges, like total charge applied to the system and applied to the test charge. So I mean that's compared to like different animals. You have at least a fixed one physical quantity to compare the Coulomb force as apple to apple, right? If you have changed like either should total charge same or charge density same. If you charge density same, then obviously the area is much more total charge, right? then that produce that. It also depends, just like if how that effective charge applied to this test charge, or more if it is bigger than that the point charge of single particle, then obviously that produces more Coulomb force. But you have to do some kind of you know mathematical derivation to drive the Coulomb force formula with a different type of charges. So it's
Oh,
pretty much depend on the volume or of the your the object with the charged uh, charges.
yeah. In the answer key, it didn't do they said they didn't need to do any math. They just said that using like logic, like the 2 points is gonna be the greatest because the total charge is concentrated in one spot.
Yeah,
Um,
that's what I'm saying.
and then the ones that have a straight line
Hmm.
um and or like a curved line from a single point is gonna be smaller because the charge is more spread out. And that was why it's less than the just the two particle system.
Well, I have to take a look at the problem, but as I already described, assuming that you have point charge and the single line and area, and you have all the total charges are same, then obviously the charge density applied to the test charge is lower by dividing the total charge by the area or line. So the field from the single line to that point charge will be less from a smaller charge density. I mean, smaller actually charge. So if you have, so what kind of like line are you saying? That's like enclosed of the line around the point test charge. That's the
It's like two particles vertical. And then there's a situation where there's like a line on top of like the particle, and they're like the same distance away. And they're both the bottom particle is Q and the top line is 2Q, and then the top particle is 2Q. So it's just comparing those two situations.
well. Well, why don't you just send me the picture, and I'll take a look and give me the constraint. I can't answer that that without any detailed information of that the charge conditions too. I mean,
Okay.
obviously, it just that's the basic rule of thumb. If you have like a total charge same, but with the different shapes, like different uh, topology, like line or area, depending on the what kind of like charge distribution you have on the test charge, then you end up with a different amount of like a Coulomb force exerted on your second, charges. But that's what I'm trying to say. That's if you have constraint of the same total charge on the object, then all you need just divide the area by divide the charge by the area or line. Then that give you the effective charge producing that the Coulomb force. Okay, so you have like a total charge. As I keep saying that, you have the same total charge, but that's that distribute over a wider space. Then the charge created like electric field will be much less the charge, right? So if you just have, let me just give you one good example. Now we have one charge, two charge, Q and Q, and now you have one charge, and now you have like 10 point charges. They are create the line. So, but the total charge from here to here, same Q. Now you got to divide, in order to estimate the charge of individual point, then you got to just divide Q by 10, if it's 10 particles, right? So the Q of 10, Q of 10, there's you have 10 different, uh, you know, the 2 over 10 charges. But if it has symmetry, then the field from all this particle except the middle one will just cancel out, only produce this charge, electric Coulomb force. So there's like a small amount of field this direction, small amount of field this direction, but they all cancel out, only leave this directional field, but they're small because your charge on this one is 10 times smaller. So the Q, if you calculate the Coulomb force out of this charge, then Q times Q out of 10 of like same distance R squared. So that is 1 of 10 times Q squared of R squared. But this one is Q squared of R squared. 4 pi epsilon naught and 1, and that same thing for, 4 pi, 1 over 4 pi epsilon naught squared, right? So you end up with a 10 times smaller Coulomb force than this 2-point charge.
Mm-hmm. Yeah, that makes sense now.
So it depends on how much that your test charge is total charge distributed in the given space.
Mm-hmm.
You have to just find out the charge density first out of your given condition. Does it make sense?
Yeah.
Okay. So let's move on to our topic for today. So I'm going to move on to the Gauss law. Let me switch the color. So did you school started already this time, Gauss law? Or
Yeah, we have our test on it this Friday.
this Friday? Tomorrow,
Yes.
day after tomorrow?
Friday is in 3 days later. Yeah.
Okay. So the Gauss law is describes the electric field coming across the like given space. So if let's start with the electric flux. So the electric field is passing through some sort of like a surface with a random direction. Then usually the area vector defined by the normal direction of the surface of cross section. So if you set up the x, y, z coordinate on surface of the Gaussian surface, then that should be this normal direction perpendicular to the surface of the area. So now assuming the electric field going through this area, then usually this flux of electric field defined by field times area of interest. So now this electric field could be decomposed into the two coordinate axis, the xy. So that could be ex and ey. If the electric field has angle with the respect to normal direction of x, then usually the field component, this electric field could be expressed with the ex times delta A. Here's ex dot product could be magnitude times delta A times cosine theta. So as you know that this delta, ex is electric field times cosine theta. Okay, so that is the flux of the field passing through the area of interest. So based on that dot product, definition of dot product, if you have multiple flux line coming through this area of interest, then total flux oops, total flux is sigma summation of individual field flux, electric field times effective area of delta A. So now you have large area of interest and you have a small area of delta A, then field, coming through this area is electric field E. And this is the delta E times, electric field times delta A. Now, you need to actually just add all the surface area to find out how many actually field going through this total area of interest. So in that case, you have to add all of them with the sigma notation. So that's why I put the sigma summation to find out the total flux density, total flux quantity. But this case, I divide the area with the finite number of the small delta AI, small area. But if the area of this electric field passing through have continuous variation, so if you make this small element, the area element is just smaller and smaller and smaller, then this sigma notation and delta should be replaced with the integral, because that small, making the area smaller is effectively same as the estimating the electric field with coming through this total area with continuous variation. So the continuity of electric field should be applied to the total area of integral. So if you replace this finite number of the area sigma summation with the integral notation, then total flux cross the area should be integral of electric field dot product dA. So this is more genetic definition of the flux, total flux of the area of your interest. So in case you have some sort of a closed surface of any arbitrary random the space, so this is some kind of like, could be a sphere or it could be like a box, but let's just pick up the some kind of random shape. And if the electric field passing through this closed space, it's hard to actually draw this object, because this is three-dimensional object with enclosed surface. So, but if you assume that electric field as going through this enclosed object, then depending on which surface you're looking at, that quantity of flux could be positive or negative. If you look at this area, then electric field is hard to actually see. So if you just have like this one cross section, so the field as getting into the air, this object, so that is just inward, and the field coming through this area element of interest, field as it's just going outward. So if you estimate flux elements in this area 1, this might be like barely touching the bottom of this area. So this is 2 and this is 3. So number 1 flux element passing through this area, then field and area, this is area vector of number 1, and field actually going into this direction. So dot product of if you just look closely at this area, then it should be like this. And fill this direction inward, but area vector and this direction, and the theta. So that's the A1 and dot product electric field inward should have negative value because they're more than 90 degree. So that should be smaller than 0. So, but if field coming out of the volume of interest, then their area vector A3 and the field vector, they're same direction, only like the same, at least less than the 90 degree. So if you apply dot product of this area, then that should be cosine theta, that should be larger than 0. So if you just actually estimate the this flux, sign of flux, then you can tell that field actually inward or outward the area, I mean the volume of the interest. And if this field is just barely touching the surface of the volume of interest, then their direction is 90 degree. I mean, obviously you can see that the field is barely touching this direction, tangent direction, but the area vector is perpendicular to this area, so that angle between the dielectric field and the area vector 2, there's 90 degrees. So if you apply that dot product of these two vectors, then that should be electric field A2 magnitude the cosine 90 degree, that should be equal to 0. So the flux delta 2, I mean the flux as the area on the surface, the electric field barely touching, then their flux should be equal to 0. So if you just integrate that flux over the surface, and if there's no charge inside of this area of volume, then obviously this flux 1 plus flux 2, I mean the flux 2 and flux 3 should be equal to 0. So now it's just actually simplify this notation, but if you do that whole surface of this area, I'm sorry, let me just re-express this one. So this, if you use this one with the integral, so if you do this, now you can split this surface with the infinite number of area element, then that should be always equal to 0 as long as there's no charge inside of the surface area E and C. Okay. Do you understand what I'm saying? So if there's no there's no charge component inside of this enclosure of interest, then whatever electric field, I mean the electric flux integrated negative direction should, that total quantity across this half of this area should be exactly same as the electric flux integrated over the half the other positive, integrated electric field in positive directions. If you just sum them up, then the total net flux across this Gaussian surface of the enclosure should be equal to 0.
Wait,
Okay.
why does it matter? What if there is a charged particle inside? Does
Oh,
that...
I'm gonna go moving on to that topic right now. So if their charge, I mean, obviously there's electric field already existing. So if there any type of charge inside of the Gaussian surface of the enclosure, then this will produce the more, extra charges, extra field. Then if you integrate the flux of the whole surface, then this outgoing, the field will include the more flux electric field in given area. So phi 3 will have probably positive the flux, but that probably will have more flux than the 1, because that field you have negative direction, then that field from the oval surface integrated, then that should have number 1, number 2, number 3, and number 2. So basically this field positive direction, but that has negative, electric field. So if you add them together, this delta, that the flux out of this area, surface area of positive direction, always larger than the flux to the negative direction. So if you just add them all together, there's always larger than 0, as long as you have any charges, net charge inside of the enclosure. So this is how you can actually find that the total amount of the charges. If you integrate the flux over the Gaussian surface and multiply that the epsilon naught permittivity, and if that is non-equal and have finite number, then that should be same as the net charge inside of this Gaussian surface. So whatever field, so let me redraw it. Hold on. You have Gaussian surface of interest, and you have point charge enclosed by this surface, and that produce electric field and there's like a small area, and that produce that field that dA. And now you find that the quantity of the flux in a small area, and you know how much field actually coming through this small area. Now you just integrate the whole surface of this enclosure and add them all together. That amount of total flux times permittivity should be exactly same as the charge inside of this enclosure. So if you generalize this expression, then it should be epsilon times integral of enclosure electric field dot product area vector dA is same as the net charge E and C. So either you know the field distribution in given space, and now you know that function of area vector, then you should be able to find how much field, how much charge existing inside the Gaussian field. Or if you know the total amount of charge, and you know that the expression of the area vector, then you should be able to find how much electric field possibly generated from this Gaussian surface of the Gaussian enclosure. So most typical case is the sphere, because sphere has constant radius. You can easily find the function of the surface of the sphere. So assuming you have plus charge in the middle of a sphere, that sphere has radius r, and obviously this positive charge produce that electric field radially with the uniform electric field. Oops. Hold on. We're stuck. Okay. So the uniform electric field with the constant magnitude. So the radioelectric field component, they're all same. Regardless of which direction you're looking at, their electric field is all same with the same magnitude, and the radial vector is same too. I mean, the area vector is same too. So now we want to find out the electric field expression with this integration of the electric field over the surface of the sphere. So that is epsilon volume integral, surface integral of electric field and dot product of dA. Now you have point charge Q, that is Q and C. Now the Q, E and C is the same as Q. And this one, as I said, this electric field is this uniform constant magnitude with the radial component. So if you replace it, then there should be ER, the product, and dA, that dA R vector 2. So that's the same. So now our product, the dot product of the radial vector, unit vector of the radial direction is the epsilon and integral of E A R dot product of dot product, and that is 1. And this one now, as I said, electric field is constant value because that uniformly distribute in radial direction, so that to be out of this speed, I mean the integral. So that is epsilon electric field surface integral of dA, and this one is the surface area of the sphere. Okay, that is normally 4 pi r squared of sphere. So now that is epsilon 4 pi r squared. Electric field is same as Q. So now if you re-express this electric field and you move this term to the right hand side,